In this video, what I would like to accomplish with you today is to go through the process of diluting a solution and also to do the very simple math that goes along with that. Normally, you would be in the lab, you would be using what we call pipettes and volumetric flasks and all kinds of fancy glassware. Once again, I am going to dummy it down in simpler terms based on the glassware I have available. And the concept's still the same. We just may not be quite as accurate today. So the last lesson we talked about what a solution is and how to determine the concentration of it. We introduced the idea of the new mole triangle, N equals C times V, which I have on the board behind me. We'll need it again today. And now we're going to simply take our concentrated solution and perform a dilution. And of course, remember, we use cupric nitrate as our example, beautiful blue solution, and we can actually see what happens to the physical characteristics of that solution when we dilute it. So here we go, diluting solutions. Well, oftentimes when a chemist makes a standard solution in the lab, he or she realizes that that solution will be ultimately used by others and likely get diluted. It's impossible to concentrate a big solution unless you decide to boil it down, and that's just too hard to do. So we make concentrated solutions or our stock solutions, and then we dilute them down. So it's pretty common practice for a chemist to dilute a stock solution in the lab by adding distilled water. Remember, tap water doesn't work. It's full of impurities, chlorides, calcium ion, magnesium ion, maybe iron, manganese, whatever. Let's not go there. We use distilled water. We have our concentration triangle. Remember, N is moles. That's on the top. And C is concentration in moles per liter. Remember, that's molarity. We will use big M quite a bit. And volume is in liters. So there's our triangle. Well, if we dilute a concentrated solution with pure water, if you think about it, we're not changing the number of moles present in that original solution. All we're doing, per se, is diluting those moles. The water doesn't change the amount of copper nitrate that was there originally. It just dilutes it. Similarly, Kool-Aid, if you have an original Kool-Aid solution and you dilute it, all the original Kool-Aid is still there, it's just got more water that waters it down. So that allows us to assume that when you dilute a solution, the original moles that you started with are actually equal to the final moles in our dilute solution, because all we've done is add water. And if the moles are equal in this triangle, then C times V must be equal or constant. And that's the very useful dilution equation. C1V1 equals C2V2. Now, how can we put this into action? Well, I happen to have a concentrated cupric nitrate solution right here. And I know what volume this is. We're going to calculate that solution, and I've got a bigger cylinder with water in it. Now, I'll be honest, this is my tap water. Let's imagine that it's distilled water. I have to tell a million lies when I'm in my own house. Unlike the lab, we don't have the luxury of good distilled water. Now, set up our math. I think a picture is worth 1,000 words. So I drew my best attempt, I should say, at a small graduated cylinder. This would be our original stock solution that I just showed you, and the final cylinder, which would be the diluted solution. V1 is unknown because the question says how many milliliters of our original 0.5 molar cupric nitrate solution are needed to prepare 250 mils of a 0.1 molar solution. So that new solution is quite a bit more dilute at 0.1 moles per liter than the original one was at 0.5. So we know that the final volume is going to be larger than the initial. We know the final volume is 250 mils. Let's convert that to liters. And we know our final molarity is 0.1 moles per liter, or big M. Now we do the math. It's very easy if you think about it, because we have our equation. C1V1 is equal to C2V2. If we rearrange that equation, then we get V1 is equal to C2V2 over C1. Cross multiplication. You've all done that. And we plug it in. We have our C2 at 0.1 mole per liter, our V2 at 0.25 liters, divided by our original concentration at 0.5, and we get 50 milliliters of original solution. Now, what does that really mean? Well, I just happen to magically have 50 milliliters of our original solution. It's almost like I know what I'm doing. And you can see we have about 200 mils of water. This is a weird cylinder. Frankly, haven't seen one like it. It measures 190 and it goes up by 10 every 10 units instead of on the zero for 200. But regardless, I have 200 mils in here. And if I add this concentrated solution to the water, then we obviously dilute it. And you can see as I add it that that's happened. The blue solution that we started with is not as concentrated now as it was before. And our final volume, sure, is about 250 mils. So very easily we have achieved our dilution. Now, if you really analyze what we just did, we took 50 mils of the concentrated cupric nitrate and put it into a cylinder, and our final volume was 250 mils. We also could figure out how much water was involved. Even though the question didn't ask that, you saw me do the demonstration. In the end, it kind of makes sense that if V1 is 50 mils here, which we just figured out mathematically, and we have to end up with 250 mils, it stands to reason that we needed 200 mils of distilled water in that flask. So that is a good look at dilutions. We can take a concentrated solution and add water to it and dilute it to a more dilute solution. We could actually dilute this further if you think about it. There's still quite a bit of cupric nitrate in here. It's 0.1 molar. We could do a number of dilutions on this solution. That's known as a serial dilution. Again, in the lab, we would carry this out. You'll just have to imagine me doing it here virtually. So, that's a quick look at diluting solutions. C1V1 equals C2V2. And I hope it's not too difficult for you. This is our last topic in Chapter 8. We're not going to look at extremely low concentrations. And our next stop is Chapter 9. And we'll get into looking at solubility a little bit more and breaking soluble compounds down into ions, and we'll look at the whole process of solubility, and that'll lead us into Chapter 10, which deals with acid-base chemistry. Until next time, hopefully this helps, and continue on with your learning. Enjoy it. The weather's been a little bit iffy outside, and that's maybe a blessing in disguise. We can do a little more work and not feel so bad about being inside.